Today I want to do a little video about inverse functions, section 3.7. And we've talked about inverse functions. We've mentioned them a few times. What we're doing is it's a kind of reversing function. If you have a function that takes an input and gives you an output, say it gives you plug in the time and it gives you the cost, then an inverse function would take the output, the cost, and reverse that function and give you the time that you started with. So it's a reversing function, and if you switch the input is normally x and the output is y, then the function, the inverse, would say, given the output, output, reverse the function and find original input. Visually, like these diagrams we've been talking about in the past, if we have a function that takes from the domain to the range, it takes f over to f of x, then what you'd want in an inverse function is if I tell you the value that I got as an output, if I tell you I got out y, the inverse function should take that y as an input and reverse it and tell you x, which was the original x you started with. And so we've talked about it a couple times. If you compose those two functions, you plug in x into the function, then you do the inverse function, f inverse, and it gets you back to x where you started. It undoes the rule that you did. So here's a definition. Here's the formal definition from the book. It's f inverse x is an inverse function if f inverse of y equals x. So notice they switched the x and y in here in terms of they switched which one is the input, the dependent variable, and which one is the output, the independent variable. So as you do this, it's exactly what we've been talking about, and they talk about here that f minus 1, you read it as f inverse. It's not the negative 1 power, not the negative 1 power, which would be a reciprocal, like this. If you wanted to do that, I think the best way to do that would be big parentheses and a negative 1 outside. But if the negative 1 is inside there, kind of tucked in between the f and the parentheses x, that is always represented to be an inverse function. And so in the book, they describe a three-step process to find the inverse function. Find the inverse. 1, you make sure the function's 1-to-1, and I'll explain why that's important in a second. Second, you solve for x. And third, you interchange x and y. And I want to point out why that's not a very good way to explain inverse functions, even though that's what every textbook does. Here's a question. In the book, the very next example is converting Fahrenheit to Celsius and doing the inverse of that function. So here's the function they tell us, and that's what we talked about in class on Monday. If you plug in a degrees Fahrenheit, you subtract 32, then take 5/9 of that, and that'll give you C, the Celsius. So if we want to find the inverse of that function, the first thing we have to do is solve for x, but there's no x there. You can't even start. So I'm going to hold off on that in just a little bit and explain what I think is a better way to explain this process. But let's do one where it is just normal x's that you're used to. So let's say we have this function here. F of x equals 7 times x minus 2 cubed plus 5. We want to find the reversing function, the inverse function. Then let's think about this. First thing they check is it's 1-to-1. And we've talked about that a little bit. Cubed functions turn out to be 1-to-1. But let's solve for x. So let's do this, and we have y equals 7 x minus 2 cubed plus 5. If you're doing this function, what's the process to evaluate that function? If I told you to plug in x equals 17 for this, first you would subtract 2. Then you would cube whatever you had. Then you would multiply by 7. Then you would subtract 5. Right, in that order. What happened if you want to reverse that? reverse the function. Think about those four things in an order, and the last one you did was add 5. Oops, add 5. Add 5. The last thing you did was add 5, so the first thing you have to do is subtract 5. And then before that you multiplied by 7, so to undo that you divide by 7. Then you took the cube, so to undo that you have to take the cube root. And then the first thing you did was subtract 2, so the last thing you have to undo is that. And so you reverse these functions, you undo them, but in the reverse order. And that's exactly what you do when you solve this algebraically. You'd first subtract 5, and then you would divide by 7, and you'd get y minus 5 divided by 7 equals x minus 2 cubed. Then you take the cube root. You take the cube root of both sides, y minus 5 over 7 equals x minus 2. And then the last thing you do is add 2. Cube root of y minus 5 over 7 plus 2 equals x. So, and then the way they in the book just tell you to write it, which I'll explain why I don't think is a great idea, is to then write it as f inverse of x is cube root of x minus 5 over 7 plus 2. They tell you to switch x and y, so you change this variable back to an x. It was a y, you make it back to an x. Their rationale is we're used to our function always being a function of x, but that's a kind of arbitrary thing, and I'll show you in an example why that doesn't always make sense. The better way to think about it is you start with x as an input and y as an output, and you want to solve for x, the input, so that if I tell you down here that I got an output of y, here's the rule: I subtract 5, divide by 7, cube root it, add 2, and I get x, the original number you started with. Here's an example, back to the Fahrenheit and Celsius, where there's no x's and y's because f and c actually have meanings, and they have they're not abstract variables, they have meaning. So this function, c equals 5/9 f minus 32, the input is Fahrenheit, degrees in Fahrenheit, and the output is degrees in Celsius. And so if you go and solve this, you want to solve for f. The inverse would have an input c and output f. So I want to solve for f. F equals something. That's my goal. So how do I do that? Well, the first thing I would do, if I start with c equals 5/9 f minus 32, I would multiply by 9, f minus 32. Then I would divide by 5. Whoops, let me write it in a separate row here. 9/5 c equals f minus 32, and then 9/5 c plus 32 equals f. That's my formula, right? The Fahrenheit is equal to 9/5 c plus 32. And if you follow the guidelines that they have in the book, they would tell you to switch x and y. So switch the input and output. So you get c equals 9/5 f plus 32. But that's wrong. When f and c have specific concrete meanings, this equation's wrong. So just leave it as is here. You have found the formula that takes plug in Celsius and you get out Fahrenheit. And you started with a formula that says plug in Fahrenheit and you get out Celsius. That's exactly what you want to do. The next thing I want to talk about is what the graphs of these functions look like. And there's another concept that every book talks about that I disagree with, and I will explain that when we get to it. But here we've got two functions. We've got f of x and g of x, and they ask, is g actually the inverse of f? And you can check that. You can check f of g of x, is that x? Because that should be in the case that you apply g of x, and then you the output you get from that, you get f of x, or you plug into f of x and you get back to where you started, or x. And it should go in either direction. If you start with f, I can't write today, and then do g, you should get back to where you started. So if you compose, it's like changing Celsius to Fahrenheit, then Fahrenheit back to Celsius, or Fahrenheit to Celsius, then Celsius back to Fahrenheit. Either order of those operations gets back to where you started. You can double check that, just plug those in and check. Or you can think about the order of operations. F says you do what first? You take a value, you subtract 1, and then you cube it. So if you wanted to undo that, you would take the cube root and then add 1. That's exactly what this function is. So you can do that. But let's picture the graphs of these. So we talked about this in the last time. F of x is x cubed minus 1. Well, y equals x cubed is just this function, something like that. And if we do the minus 1 inside, that's a shift to the right. Over, so the center of the x cubed function moves over to 1. And so then all the rest of the curves follow along, and you get these points 2, 1, 3, 8, 0, minus 1, and negative 1, 8, negative 1, negative 8. And so for example, I could take f of 0 is minus 1, f of 1 is 0, f of 2 is 1. So now, magically, let's go across to the inverse side of this. That's going to be g of minus 1 should be 0. Since f of 0 is minus 1, I input 0 and get out minus 1. If I tell you my output was minus 1, what number did I start with? It must have been 0. And then g of 0, what number do I plug in if I ended up getting out 0 as my answer? It must have been 1. And what's g of 1? What number did I plug into f to get out an output of 1? It must have been 2. So all those give us points back up on the curve. Minus 1, 0. Minus 1, 0. 0, 1. 1, 2. 1, 2. And I could plug in the negative ones here too. So what would we get? Let's say g of negative 8. What's g of negative 8? Well, what number over here would give me an output of negative 8? It's negative 1. So if I go over here to negative 8, I'm going to be at 1, or negative 1. And you can fill in more and more dots on this. 3, 8 up here in the corner corresponds over here to 8, 3. And if I fill it in, I can get a curve like that. And what happens, so typically all you're doing is switching the input and output. So in this case, the 8 is the output and the 3 is the input. So the 3 is on the horizontal axis and the 8 is on the y-axis. And now when I do the inverse, I've switched, and the 8 is now the input into the inverse function. And the 3 is the output. So the 8 is now on the horizontal axis, and the 3 is on the vertical axis. All I've done when I switch the input to the output of any specific point is switch whether it's on the x-axis or the y-axis. So I've kind of flipped the curve, and it went from the blue curve over to that red. You can then double check, like I said up above. You can do this double check and plug in the function. So I have the negative the inverse in the wrong spot here. So if I want to take the function and plug in the inverse, all I do, the function says I want to do x minus 1 cubed. And I plug in the purple into that, f of x. F of x is just cube root of x plus 1. And what happens when I simplify that? Well, I get cube root of x plus 1 minus 1 goes away, cubed. And cube root of x, or x, the cube root of x cubed is just x. So I get back to f of f inverse of x is x. That means, so they are inverse functions. Technically, we should check f inverse of f of x, which is f inverse is the cube root of something plus 1. What do I plug into that something? I plug in the other function, which is x minus 1 cubed. The cube and the cube root cancel, so I just get x minus 1 plus 1, and I get x. I get back to the original input. That is the definition of what an inverse function is supposed to do. Here's one last example. Suppose we have a ball and we drop it from a high height, 64 feet in the air. And I want a formula. My physics professor friends tell me this is the formula for the height, t seconds after we drop it. And that's a parabola. And doing our transformation things, we've got this minus 16 is going to be multiplying the standard parabola by 16, which makes it a tall, skinny parabola, and then multiplying that by negative 1, which flips it upside down, and then adding 64 to it, which takes it up, moves it up 64. And we end up with this blue parabola shown. And I've plotted some points that they'll be on there. It's up at the top at 64, and then as the ball falls, after 1 second, it's at 48 feet, and after 2 seconds, it's landed on the ground. Okay? So what would an inverse function mean in that case? Well, an inverse would be the function I have is you tell me the time, and I can plug this rule in and get an answer for the height. An inverse would be solve for t. So I would get t equals something. What's that going to be? Well, I would subtract 64 equals minus 16t squared, and then I can divide by 16, h minus 64 over negative 16 equals t squared. T equals plus or minus the square root of h minus 64 over negative 16. And I'm going to simplify this just a little bit here. 64 minus h over 16 just looks nicer, gets rid of that negative in the denominator. All I did was multiply top and bottom by negative 1. But here's my answer. And what do you notice is wrong? T is not a function. T gives me plus or minus. So it's technically not a function the way it's written. Not a function. And it's not a function because the original thing was not 1-to-1, right? The original parabola is not 1-to-1. If you tell me a height, say 48, there are 2 times when I'm at 48. H of negative 1 equals 48, and h of 1 equals 48. It violates the horizontal line test. So it's not a function. What's our save here? How do we save ourselves? Let me copy this and paste it in here. And what's the way to save the problem here? Well, the way to save it is in real life, the domain of this is only positive numbers. Domain is t has to be positive. Right? If you're dropping the ball, what was the height 2 seconds before you dropped it? It doesn't follow this formula. So when I solve the inverse, I do the same algebra all the way down here, but when I get down to the plus or minus, I just take the positive one. All I care about is the positive value. And so it is a function. Is a function now. And let me erase this over here. The parabola, so the half a parabola, is a one-to-one function. If I'm just looking at the piece of the parabola, I can actually delete this down here, because the domain is not t equals, the domain also stops at 2. So the domain is really 0 to 2. I should be more careful with that. But the point is, if I restrict the domain to the relevant values for this problem, it is one-to-one. If I ask you, find when it was at a height of 48, h equals 48, there's only one answer, t equals 1 second. And it does pass the horizontal line test. So all that is saying, if you have a function, if you graph it, you want to draw or think about the inverse, it has to be a one-to-one function in order to have an inverse. And last thing I'll do is draw these. We had the parabola is this, and it goes from 0, 64 down to 2, 0. And this is time, and this is height. And in the book, they talk about then if you draw the inverse function on the same set of axes, if you look at this function, the t function, t equals the square root of 64 minus h over 16. If you graph that, it'll look like this. This is out here at 64, 0, and it comes here at 0, 2. All I've done is switch the 2 and the 0, and so that's flipped kind of across this diagonal axis. But I want you to be careful about that, because the books always say draw the two things on the same set of axes, and you've got this symmetry to the half of the parabola and the square root function. They're symmetric. I didn't draw them to scale, but they're close. But you don't really want to switch axes, just switch axes. Since now, in purple, this is the height axis, right? 64 is the height, not the time. And this is the time axis. So you can't just abstractly flip the graph if the variables have concrete meanings, if they have height and time, or cost and number of units sold, or whatever the input and output are. If it's a practical problem, you don't actually want to flip the axes, but you can think about them in that way.